Hello everybody, and welcome back to Calculosity with your host Corey. Today we're going to be talking about limits with algebraic manipulation. That is, when we have to manipulate the algebra in order to calculate and get a good, usable response from the limit calculation. So remember previously when we calculated the limit back a couple episodes, when we calculated the limit as x approaches positive 1 of x minus 1, divided by x minus 1 times x plus 1. This limit is problematic because when we plug in the positive 1, the numerator gets zeroed out, and so does the denominator. We end up with an answer of 0 over 0. And that is completely and utterly unusable. That is because this is considered an indeterminate form. And this is an important term to remember, indeterminant. So this is an indeterminate form. It means it is unusable. This doesn't give us any valuable information. So let's work with this. Let's see if we can do something to get an answer that is usable. And so whenever we come across an indeterminate form, which is, I'll outline them now, 0 over 0, that is an indeterminate form. We also have forms like infinity minus infinity. That is a problematic form. Infinity to the 0 is a problematic form, as well as 0 times infinity. These are problematic. We don't want to mess with them. If we get them as an answer, we need to be careful and do some simplification before we can actually get a viable numerical answer that is either A, negative infinity, positive infinity, or D and E. It does not exist. So if we get any of these, it means we have to go a step further. We have to go further. So if we get any of these, which we do on this previous problem, we have to simplify. But it's pretty obvious what's wrong with that problem at the top, and that's that we have an x minus 1 term in both the numerator and denominator. And that's because this is called a removable discontinuity, which we discussed briefly, but it's not important that we know what it is right now because we will be discussing discontinuities as a whole a little bit later in a couple episodes. So what we're going to do here then is cancel those out, and when we cancel those out, we get a new version, that is x divided by x plus 1, or rather the limit thereof. And if we take the limit of that as x approaches 1, we end up with something that is a lot more usable, and that is 1 over 2. And so that would be our answer. And that just meant, when we got the indeterminate form, that we had to simplify and get it a step further. That is the algebraic manipulation, that we're manipulating the algebra in order to get a viable and usable answer. So, that being said, then there are a couple different times in which we have to do algebraic manipulation. Frankly, it's any time we get an indeterminate answer. So a very, very common one that you're going to encounter when you get into derivatives is this particular situation. You'll become more comfortable with what this formula is in a short while. But let's see here. Say we have the square root of x plus h minus the square root of x over h. This is a problematic form because if we do the limit as h approaches 0, it means we just plug in 0 for h. We get square root of x minus the square root of x, which is 0, divided by h equals 0, an indeterminate form. And a very, very common and very, very useful way that you're going to be doing quite often once you get into the long definition of the derivative, which we'll get into in a couple units. That's nothing to rush into. You'll be very comfortable with using this particular tactic of algebraic manipulation in order to get to a determinant form from an indeterminate form like this one. And that is called multiplying by the conjugate. That is a very important form of algebraic manipulation. So multiplying by the conjugate. I still can't write. Alright, so multiply by what they call the conjugate. So what is the conjugate, you ask? Well, you're going to get very cozy with the idea of the conjugate right now. And so we're going to go over what exactly is the conjugate. Well, the conjugate is, in layman's term, the same thing but with an opposite sign. So in this case, what we're dealing with is the square root of x plus h minus the square root of x. That's what's giving us the big issue, because it gives us a 0 on top. Now if that were a 1, we'd know it's d and e. And if we were able to somehow also change the denominator, then that would give us a viable answer. So we really want to get this numerator to look good. So this is the issue right here, is this numerator, this x plus h minus the square root of x. So what we can do here is play a little interesting tactic, multiplying by the conjugate. Know that you can multiply a fraction by 1 over 1 and it does not change the value ever. It's going to be exactly the same thing. But remember that 1 over 1 can be represented in a bunch of different ways. 1 over 1, or 1, is represented as anything divided by itself. So we can multiply anything divided by itself into this fraction, and it will not change the value. And we're going to use that to our advantage to get this into a determinant form. So what we're going to do is we're going to multiply by the conjugate, which is the exact same thing with the opposite sign. It's going to be the square root of x plus h, but now we're going to be adding the square root of x and dividing by the same exact thing, the square root of x plus h plus the square root of x. When we do that, we effectively change this subtraction, which is problematic because it causes terms to cancel, into addition, which is no longer problematic because nothing is going to cancel. So we can expect this is going to clear up our issue. But if you want to understand more thoroughly why this is going to cause a good cancellation, it's because this is a sort of reverse engineering of difference between two perfect squares, which is a way that we factor things. If you're ever familiar with encountering a problem like factor x squared minus 4, well, we know x squared is the square of x, and we know 4 is the square of 2. And so by difference, which is the subtraction of two perfect squares, we can break this into two terms, that is x minus 2 and x plus 2. What we're doing here is the exact same thing, except now the x minus 2 is that mess over there, the square root of x plus h minus the square root of x. That's the x minus 2 in quotes. And the x plus 2 is the conjugate that we're multiplying in. And so by doing this, we're able to get this square in there. By being able to square the square root and getting rid of the square root, it allows us to combine terms and manipulate it in such a way that is a lot more useful. The more general way to look at this difference between two perfect squares is that we have the first term, it's going to be some sort of square. We can look at it as a squared minus b squared, for example. That's going to factor into a minus b, a plus b, right? So, if you look at what we're doing over here then, the a term is this guy. The b term is this guy. So our final output is going to turn out to be a squared minus b squared, which is going to be x plus h minus x. And of course we have all the other mess in the denominator from the conjugate that didn't cancel anything out. It just gets next to the h. But we're not even going to have to worry about simplifying that because it's going to work out really nicely, as you're about to see. So the x minus x is going to cause complete cancellation of these x terms. And don't forget that we are still calculating the limit. That is the problem we're trying to solve here, so we can't forget about that. Oftentimes students like to drop the limit symbol and leave the h's in, which is not acceptable. So now that we have this cancellation here, it gets a million times less complicated, because now we end up with this, the limit as h approaches 0 of h divided by h square root of x plus h plus the square root of x. So we should see immediately that there's another cancellation, and that's going to be those h terms. These guys cross right out. And now it's not so spooky, because we can absolutely plug in h equals 0 into this limit, and all of a sudden we end up with, now that we've calculated the limit, we don't have to worry about the limit as h approaches 0 anymore. A lot of students also like to leave that in. So now we can just have 1, because we cancel out the top h, and we cancel the bottom h, so now we just plug in h equals 0, and we get the square root of x plus the square root of x, which is 1 over 2 square root of x. And yes, I know there's still a variable in there, but we need to remember that we were calculating the limit with respect to h, and there were two variables in the beginning, so it is acceptable to still have a variable left over, since the limit only applies to one at a time. So we have 1 over 2 square root of x, which you will learn later is the derivative of the square root of x. But we're not there yet, so don't you worry if you don't understand a thing that just happened. What's important is that we know that the conjugate will cancel out oftentimes, especially when we're dealing with the subtraction of square roots. It will cancel out any of the issues causing indeterminate answers. But there is another way to deal with indeterminate answers that we're going to delve into next. yet another fun way to manipulate algebra. And this one is also extremely important, and it is called squeeze theory. Sounds fun, and it is. So squeeze theory. So now we're going to jump into squeeze theory. This is a fun theory, fun to say, fun to talk about. So, what squeeze theory is, it's when we have an answer that comes out that doesn't look so great, an indeterminate form like the other ones, but we're not able to use the simplification tools that we use in the other one, like the conjugate or any other type of simplification, in order to get into a determinant form. What squeeze theory allows us to do is to pin a limit between two other known limits. So if we say something is greater than or equal to something that we know, and less than or equal to something else that we know, if we're able to pull those two things we know together, and get the same value for them, and pin that limit that we want to know in between them, we're able to determine what that limit's value is. So let's look at a good example of squeeze theory. Let's look at the limit as x approaches infinity of sine of x divided by x. So this one is troubling. And why is it troubling? Well, it's troubling because sine is, well, does not exist. You cannot calculate the limit of sine as x goes to infinity, because that gives you something like this. Does not exist over infinity, and that is difficult to reconcile. It doesn't work so well. But because we're dividing by infinity, we know that that's going to probably end up overpowering the sine of x, because it is going to increase up towards infinity, and x will continue towards infinity, whereas the sine of x is going to be constantly oscillating between -1 and 1. So that x is going to drag this thing towards 0, but we need to be able to show that mathematically. So by squeeze theory, what we know is that sine of x oscillates between -1 and +1, as does cosine. And just remember what sine of x looks like here. It's constantly moving between 1 and -1. It will never ever stop. That's the reason why its limit does not exist, because it doesn't really approach a single value of y as it goes towards infinity. It just keeps going between -1 and 1. So that being said, we know that sine is pinned between these two. So if we divide every piece by x in this expression, which we are allowed to do as long as we do it to every single piece, as it is with equal signs, once we do that, we see that we have something that we can work with better. That is, -1 over x is less than or equal to it, and 1 over x is greater than or equal to it. So we've effectively pinned it between these expressions divided by x. And if we know anything about limits, we can apply them to every single piece of this expression, and it will still be equivalent. Remember, we can do anything to any piece of this as long as we do it to all of the pieces. So that means to us that the limit of -1 over x is less than or equal to the limit of sine of x over x, which is also less than or equal to the limit of 1 over x. And of course, it's as x approaches infinity. So this problem looked really problematic at the outset, but we do know that the limits on either side, that is the limit as x approaches infinity of -1 over x and of +1 over x, these guys calculate really easily. It becomes -1 over infinity, which is actually a problem we did earlier, and also +1 over infinity. And each of these is equivalent to 0. So what we have done here is we've effectively pinned the limit we're looking for between two zeros. And if something is both less than or equal to and greater than or equal to 0, well, there's nowhere for it to go but 0. It has effectively been squeezed. And so by squeeze theorem, this limit has to be equal to 0. So this is very tricky to see at the outset because we have sine of x over x, and we know that sine does not exist. But we need to be careful judging at the outset that a piece of it does not exist. We need to show that the entire thing does not exist. Otherwise, it's no good. So our conventional methods of calculating limits, they don't work here. We don't get an indeterminate form, not necessarily. So we are kind of troubled in figuring out what theorem we need to use next. But thankfully, squeeze theorem is very useful when we can pin something between two other things, and that this means it comes really in handy when we're dealing with bounded functions. Bounded functions being like sine and cosine, which run between -1 and 1 always. They are bounded, they have a top and a bottom. So if we deal with these bounded functions, these trigonometric oscillating functions, we really shouldn't jump to conclusions saying they do not exist. If we're dividing by some other value or multiplying by some other value, we should be careful to make sure that there isn't some other modification occurring that's going to cause it to converge, that's going to cause it to have a horizontal asymptote, in this case of y equals 0. So that being said, that is squeeze theory, and it's useful really quite a bit with trigonometry. So if you encounter a limit of trigonometry and you really want to say it does not exist, but you can't show why, perhaps you should take a moment and consider doing squeeze theory. Consider that it will almost always oscillate between -1 and 1. And then slowly add on pieces until what you have matches what the limit is calculating. And then see if it's stuck between two things that are going to converge to the same value. That is, that two things that have the same limit. Because if that's the case, we get something like this problem, and we have a solution. So folks, that's squeeze theory. Now we've discussed algebraic manipulation, which includes squeeze theory, using the conjugate, and really any other algebraic manipulation, anything else you can do to these functions to get them from an indeterminate form to a determinant form. Now, a lot of these are like canceling out like terms, like we saw with the removable discontinuity, or dividing by the same term in the numerator and denominator, like canceling out an x squared and everything. Things like that will prove extremely useful to us. And so that being said, now we have discussed algebraic manipulation and we're ready to move on. So good work everybody, and we'll move on to the next station. Thank you very much.